Hello and welcome to this video on how to run a confirmatory factor analysis with complex sample data in Mplus. My name is Geiser, I'm an instructor with QuantFish. So first of all, what is complex sample data and why does it potentially cause an issue for confirmatory factor analysis? Complex sampling refers to the sampling process when individuals are nested within groups. For example, students nested within classrooms, patients nested within therapists or doctors, employees nested within companies. In that situation, we have a complex sampling design, or we also call that a hierarchical or multi-level sampling design, which can cause some issues for statistical analysis, including but not limited to confirmatory factor analysis. Now, why does this issue arise? Or what problem does a complex sample come with, potentially? The issue is that observations that are in the same group or cluster, as we say, for example, students who are in the same classroom, are exposed to a similar environment, and therefore their observations tend to be correlated, meaning they are more similar to one another than to the data points that are collected from individuals who belong to a different group. Potentially, not necessarily, but oftentimes this is the case. So for example, students in the same classroom are exposed to the same teacher, the same peers, the same curriculum, maybe the same problems. If there are maybe problem children in that class, or if the teacher is sick, then they all experience those issues. And so therefore, the observations in the same group can be more similar to one another. Or another example would be couples. When you look at husbands and wives and you look at 100 couples, then those couples who are married to one another, they tend to be more similar. They tend to report similar things on their marriage, obviously because they're married and they're exposed to the same household and so on. And so therefore, what happens with complex samples is that you have correlated observations, and as a result, you are overestimating your effective sample size. So if you have 100 couples, then you don't really have 100 or 100 times 2, so you don't really have 200 independent data points, because the husbands and wives that are a couple, they will report similar data points, so to say, or correlated data points, and so therefore your effective sample size is actually smaller than the 200 individuals that you would gather with 100 couples. And so then as a result, this can affect the standard errors of your parameter estimates in confirmatory factor analysis. It can also importantly affect the model fit statistics. So the chi-square test of model fit then may be unreliable, and that is potentially a problem, and the standard errors of the parameter estimates in confirmatory factor analysis may be incorrect. As a result, for example, you may find a significant correlation between two factors when in fact maybe that correlation is not really statistically significant, because you are potentially underestimating your standard errors. So that is the issue with multi-level data, is that you can end up with incorrect standard errors, incorrect fit statistics. This does not only affect confirmatory factor analysis, it would be the same issue in regression analysis, path analysis, structural equation modeling with latent variables, and other techniques such as analysis of variance or a t-test. So how can we address this in the Mplus software? There are essentially two ways in Mplus to address this. And so one way to address this is to run a multi-level confirmatory factor analysis where you specify a factor model for each level. That works in Mplus with a two-level option. Now, this is something that I'm not going to address in this video. I have a separate video on multi-level confirmatory factor analysis on this channel that you can check out. Here I'm going to focus on the second, simpler option in Mplus. And that's an option where you specify your regular CFA as a single level model, as you would with non-cluster data or with data that is not multi-level data. And so I'm going to show you how this can be addressed. with the type equals complex option. The type equals complex option simply provides a correction for the standard errors and the fit statistics and gives you the regular single level aggregated parameter estimates. And this may be a good solution when you're not really interested in a two-level factor model, or when you don't know what model you should specify at the group level, which can be difficult to determine, and or when your level 2 or group level sample size is insufficient. And that is something that often happens because a multi-level confirmatory factor analysis requires a sufficiently large level 2 sample size, not just an individual level sample size, but you also have to have enough clusters or level 2 units. And so that is often not the case. Specifically, it is recommended as a rule of thumb that you have at least 100 clusters or 100 groups for a multi-level CFA, and that's something that often is not present. So you may only have 50 groups, and then specifying a factor model at the group level that can be, or that often fails when you have such a small sample size. And then you can still use the type equals complex option and just specify a single level CFA model, but obtain adjusted standard errors and adjusted fit statistics. Now, before I show you how to do this, I want to show you a way in which you can easily find out whether the clustering of your observations really does have an impact in terms of causing non-independence of observations. And that works in Mplus by using the two-level basic option, which allows you to compute the intra-class correlation coefficients for all variables that then you're going to use in your factor model. So you can see here in this output file, in the syntax, I specified type equals two-level basic, and I did not specify a model at all. I only listed my variables here under use variables. Those are the indicator variables of the factors that subsequently I will use in my factor analysis. But here I only wanted to find out how large the intra-class correlations are as a measure of how strong the dependency is of observations due to clustering. And my cluster variable here is group, so I'm specifying cluster equals group so that Mplus knows how the complex sampling structure, the multi-level structure, is defined here. And then I'm running type 2-level basic. And then when we scroll down, we can see that we have 1000 individual observations here. And the number of clusters here is 500. So we had 2 observations in each cluster. So this could be an example of husbands and wives. So a dyadic study where we have maybe husbands and wives nested within couples. And so when I scroll further down, we can see that the intra-class correlation coefficients are given for all 6 variables and that they're all very substantial here. So they're all above 0.3. The highest one is 0.444. So that's very strong. That's very significant variance at the between groups level. So this indicates that the observations are strongly correlated and that the multi-level structure may have an impact on the standard errors and the fit statistics in a confirmatory factor analysis. Next, we can take a look at how a confirmatory factor analysis can be specified with cluster data. And so you can see here I fit a single level confirmatory factor analysis for the individual level, but with the option type equals complex, which provides an adjustment of the standard errors and fit statistics. You can see again I specified my 6 variables. The first 3 are for the first factor, and then the next 3 are for the second factor. I have my cluster variable specified here again, so Mplus knows how the cluster structure is defined. And then under analysis, I specified type equals complex. And then after that, my model statement is the exact same as you would use in a regular confirmatory factor analysis for a random sample with no clustering and no complex structure. So there's really no difference other than that we have to specify a cluster variable and then choose type equals complex. And then what Mplus does is it uses a sandwich estimator to provide robust standard errors. This is referred to as the MLR estimator In Mplus, you can see that here, estimator MLR, if you didn't specify type equals complex, you would get regular maximum likelihood estimation with regular standard errors that are not adjusted, regular chi-square fit statistics that are not adjusted for clustering. But this MLR estimator here gives us adjusted standard errors and adjusted chi-square statistics that are robust or more robust to clustering. When we scroll further down, we can see that everything looks the same as if we were specifying this model for a simple random sample without clustering. But when you get to the model fit statistics section, you will find that the log likelihood gives a scaling factor for the robust MLR estimator for the H0 model and the H1 model. So this is different. And then also the chi-square statistic has a scaling correction factor based on the MLR estimator. So this p-value here for the chi-square is potentially different from the p-value that you would get if you didn't use type equals complex. And the p-value tends to be better with adjustment because clustering and multi-level dependencies of data can lead to inflated chi-square statistics and can then lead to a chi-square incorrectly rejecting too many models. And so here this model is not rejected. The p-value is 0.23, so at least if you're testing at a 0.05 level, then this model would not be rejected here. Also, the fit statistics are adjusted accordingly. And then when you scroll further down, the model results look the same as they would without adjustment. However, if you were to compare the standard errors in the SE column to the standard errors with regular maximum likelihood estimation, you would potentially see differences there because those standard errors are also adjusted. You wouldn't see any differences with regard to the estimates themselves. So the point estimates are not different under MLR as compared to ML. You get the same parameter estimates, but you get potentially different standard errors with a type equals complex CFA. Now, this exact same option can also be used for regression analysis, path analysis, structural equation modeling in Mplus. So whenever you have complex sample data and for some reason you cannot or do not want to specify a multi-level model, then this is an option to make an adjustment to the fit statistics and standard errors without having to specify a multi-level data analysis, which is more complex and requires a large level 2 sample size potentially. I hope you found this video useful. If you did, please subscribe to this channel. Don't forget to check out the additional resources in the description, including workshops that we offer through QuantFish, and I'll see you next time.